So it's like what we did with sodium at the beginning of this chapter. We knew that sodium is in the third energy level. So Bohr said that the electrons have to be found on these rings. So I'm never going to find an electron somewhere floating in the middle. So this is never going to happen. I can never have this. They're always going to have to be on that orbit. They're going to have to be on those circles. So that's what Bohr is trying to say. Now, we've talked about energy levels before, but I want you to look at this picture, and I really want you to pay most attention to the one on the right-hand side. The one on the left-hand side, I'm not so much concerned about. It's the one on the right-hand side that I think that you're going to have to know the most. On the right-hand side, they're showing you the amount of space that's between these energy levels. So there's a huge amount of space between N1 and N2. There's a smaller amount of space between N equals 2 and N equals 3. There's an even smaller amount of space between N equals 3 and N equals 4. There's an even smaller amount of space between N equals 4 and N equals 5. So I think about this, or the way that I teach it in chemistry, is that Bohr kind of thought about this as a ladder. The only problem is, a ladder has equal spacing, but that's not true at all in terms of energy levels. As I move farther and farther away from the nucleus. So where you're N equals 1, if you're looking at this picture with me on slide number 25, N equals 1 is what we call ground state, and you need to write that in your notes. Where N equals 1, that's ground state. That means that that's where the electron is most stable. It wants to be there because it's really close to the nucleus, and we know that electrons want to be close to a positive charge because they are opposites, which means they attract one another. So if I need to pull an electron away from the nucleus to get it up to N equals 2, I'm going to have to absorb quite a bit of energy to move that electron up to N equals 2. Once that electron gets up to N equals 2, maybe now it wants to move to N equals 3. I don't need as much energy because it's already far enough away from the nucleus that now I don't have to absorb as much energy to get up to the next energy level. So now if I want to move, let's say from like N equals 4 to N equals 5, that needs an even lesser amount of energy to be absorbed because it's already super far away from the nucleus anyway, that it really doesn't need that much more energy to get to that next energy level. Okay, so that's why the spacing is really decreasing as we go up energy levels, because it doesn't need as much energy since it's getting farther and farther away from the nucleus as it moves to different energy levels. Okay, now we can go, just like we're absorbing and moving up, electrons can also emit energy and move back down. So if an electron wants to move from N equals 5 to N equals 4, it doesn't have to emit a lot of energy. If an electron wants to move from N equals 4 to N equals 1, it's going to have to emit a ton of energy to move down, okay? So that's what these energy levels are. That's that staircase. Again, if you have questions, write those down for me, please, so then that way I can try to answer them. On the next slide, on slide number 26, it says photons are emitted or absorbed when an electron makes a transition between energy levels. So that's what we were just talking about in the last slide, where an electron can move from the first energy level to the second energy level by absorbing. It can emit energy and move from the second energy level to the first energy level, just again by releasing some amount of energy. So as the energy levels are quantized, it says the photon wavelengths can only take on certain values. So, like we said, all the electrons have to absorb a very specific amount of energy. Specifically, we've called that a quantum of energy. If it absorbs too much, it's going to be stuck in between, like an energy level, and it will never do that. So that means it can only move to a new energy level if it absorbs the perfect amount of energy, okay? Let's move on. We have 3 slides left, guys. So let's move on to slide number 27. And this is the energy required for a transition between Ni and Nf. So this just means like the electron's initial energy level and then the electron's final energy level. And that is this formula here. The energy is equal to 13.6 times 1 over the final energy level squared minus 1 over the initial energy level squared, and that EV just means that it's going to be in electron volts. We can also calculate the wavelength for the energy that's being emitted by a formula. And let me write that down. It's going to be lambda equals h times c over the change in energy. So lambda equals h times c over delta E. We know h is Planck's constant. Where are you going to get that number? At the front of your book, or in front of your test booklet. Where are you going to get c? It should be 3 times 10 to the 8th. Where are you going to find that? The beginning of your test booklet again. And then I have my energy, which is found, that energy, which is just going to be found by the equation that you were already given on that slide. Okay. Okay. I want to go on and let's do an example of one of these problems, so that way we know kind of like what they'll be asking us. Okay. This says, what is the wavelength and color of the emitted light when an electron in a hydrogen atom undergoes a transition from the n equals 3 energy level to the n equals 2 energy level? Okay. So they want to know what's the wavelength. Well, I need to know that energy before I can find the wavelength, right? Because if I think back to those two equations on the last slide, my wavelength is dependent on that amount of energy between the transition. So that means I need to find that delta E first. So delta E is equal to a 13.6. And I wrote negative here, but that's not right, so let me rewrite this. So I know my E is equal to a 13.6 times 1 over the final energy level squared minus 1 over the initial energy level squared. So I need to do this first because I need to find this. I gotta find this first. And I have to find that because that last equation that I wrote for you, that the lambda equals h times c over E. Ultimately, I want this. I have this, but I need this. So that's what we're trying to do here. So I'm trying to find that. Okay, this tells me in the problem that an electron in a hydrogen atom is going to move from n equals 3 to n equals 2. So it's moving from n equals 3 to n equals 2. So it's moving closer to the nucleus. So I'm asking you here, is this electron emitting energy or is it absorbing energy? If you said it's emitting energy, you'd be correct. If it moves to a lower energy level, it will be emitting. If it moves to a higher energy level, then that means it has to be absorbing energy. Okay, so since we're moving from 3 to 2, that means it has to be emitting some type of energy. Okay? Now, that means that at first it started out at n equals 3. So that means that my Ni, my initial energy level, is 3. My Nf, my final energy level, is going to be 2. So my initial energy level, Ni, is 3. My final is 2. So that's why we're going to plug those in up here. Okay? So let's just go ahead and plug everything in. I have 13.6 times 1 over, it wants me to give the final energy level first, and I have to square that number. So final energy level was 2. So I'm going to take 2 and square it, and then it's going to be minus 1 over the initial energy level, which was 3, and I have to square that. So this is what your problem should look like right now. 1 over 2 squared minus 1 over 3 squared. So this would be 1/4 minus 1/9. I'm going to take that times 13.6. When you do that, you should get 1.89 electron volts. So this is what you should be getting, okay? That should be your answer for your delta E. So that's my delta E. Now I know my E. Now the very last step is me trying to find the wavelength. So I know that wavelength is equal to h times c over E. My h is just Planck's constant, 6.63 times 10 to the negative 34th. My c is the speed of light, 3 times 10 to the 8th. I just found my E, that's 1.89. Okay, here's this. There's something wrong with this though, and I want you to tell me what you think it is. What would be wrong with this? Because that's joule seconds, this is meter per second, but my energy here is in electron volts, so there's something wrong. I need this to be in joules because that's in joules. So, that 1.89 that we found, we need to convert that into joules. And I know in 1 electron volt, there's 1.6 times 10 to the negative 19th joules. So that means I'm going to take 1.89 times 1.6 times 10 to the negative 19th.